Today, I will introduce our work on enhancing the harmony search algorithm to tackle complex engineering optimization problems. This research was conducted by myself, Feng Qing, in collaboration with Associate Professor Kai-King Zhou and Professor Azlan Zhang, and is presented at ICAC-2025. Engineering optimization often involves complex, high-dimensional, and nonlinear problems with constraints. Where the harmony search algorithm has shown promise due to its simplicity and derivative-free nature, it still suffers from limitations. These include fixed parameter settings, poor balance between exploration and exploitation, and a tendency to stagnate in local optimum. Our objective was to develop an enhanced harmony search algorithm, or EHS, to overcome these limitations. We introduced 4 key enhancements. The first one is dynamic selection of dimensions based on population variance. The second one is opposition-based learning to increase diversity. The third one is level flight for escaping stagnation. And the fourth one is elimination of fixed parameters for better adaptability. EHS introduces a standard deviation-guided dimension selection, meaning we explore uncertain dimensions and exploit stable ones. We apply opposition-based learning for diversity, and when a solution doesn't improve, we apply level flight to generate large perturbations, followed by greedy selection to retain only quality solutions. The algorithm works in 5 major steps. 1. Initialize a population of harmonies. 2. Dynamically select which dimensions to adjust. 3. Apply opposition-based learning to improve exploration. 4. If the update is not successful, perform level flight-based fine-tuning. 5. Use greedy selection to keep better solutions. This results in an adaptive and self-tuning net heuristic algorithm. We tested EHS on 6 classic engineering design problems. The first one is cantilever beam design, which is CBD. The second one is pressure vessel design, namely PVD. The third one is speed reducer design, namely SRD. The fourth one is 3-bar truss design, namely TBTD. The fifth one is tension compression spring design, namely TCSD. The final one is welded beam design, namely WBD. These problems differ in structure and complexity, providing a comprehensive evaluation ground. We compared EHS against 5 other algorithms, namely standard harmony search, namely HS, and the genetic algorithm, namely GA, and improved harmony search, namely AHS, and adaptive global optimum HS, namely AGOHS, and the final one is HS with cookie search, namely HSCS. Each method uses the recommended parameters from the literature to ensure fairness. EHS consistently outperforms all competitors across metrics. The first one is best quality of solutions, the second one is farthest convergence, and the third one is highest stability across 20 independent runs. Statistical validation using the Wilcoxon test confirms the significance of these improvements. In many problems, EHS reaches optimum values with minimum deviation. To verify the effectiveness of each strategy in EHS, we conducted ablation studies. We compared EHS with 2 variants. one that updates dimensions based on standard deviation only, another that uses random deviation selection. Where both improved over standard HS, the fully integrated AHS delivered the best overall performance, showing the synergistic benefit of combining both strategies. In conclusion, EHS significantly enhances the original harmony search algorithm by introducing dynamic adjustment, stochastic fine-tuning, and adaptive search strategies. It solves complex constraints optimization problems more accurately and reliably. In future work, we plan to extend EHS to large-scale, multi-objective, and dynamic optimization scenarios. This research was supported by several institutions: National Natural Science Foundation of China, Human Provincial Science Foundation, Malaysia's Ministry of Higher Education, and the Education Department of Human Province. We sincerely thank them for their support. Thank you very much. That's all.